an example right now. Okay, an example can be found, with a connection between Bernoulli and binomial. Please pay attention. Okay, now take a look at this. Let's say I want to have an example right now. Okay, let me first start from Bernoulli. Okay, Bernoulli. Okay, f of s equal p raised to power s q raised to power x minus 1, and let's start from 0 1. Of course, Bernoulli. Okay, if I derive the moment generating function for Bernoulli, mx of t, which is expected value of this, and of course a random variable. Okay, in Bernoulli follow discrete probability distribution. So I'm actually gonna have that multiplied by probability function. Don't forget, let's start from 0 to 1. Okay, so right now, so I'm actually gonna have this to that, e raised to power tx. Therefore, first is this and that. Okay, so what I'm gonna do right now, then I'm gonna have plug in 0 here. Give me 1 second. There's something that is not right. I'm gonna check right now. Give me 1 second. Oh, sorry. This should be 1 minus x. Yeah, that's not right. I didn't specify the Bernoulli very well. Yeah, because in Bernoulli, you try one time, if the number of failure, if number of success is x, so number of failure will be 1 minus x. So it should be 1 minus x. So 1 minus 0 plus T1, P1, and that. Okay. Now, when you take a look at what I have right now, so from here, okay, this is just going to be Q, and plus, this is going to be P, E, T. Now, I needed to please pay attention. Now, what I've derived here, okay, is the moment generating function of a Bernoulli distribution. Okay, if I want to know if I'm right, okay, plug in 0 to wherever you see T. When you plug in 0, I told you the other time, when you plug in 0 to wherever you see T, it should give you 1 to know if you're right. If you plug in 0 here, of course, Q plus P is 1. You know that? Okay, now, this is where I'm going. And now I want to apply this theorem here. Please pay attention. I want to apply this theorem, okay, to if I know the moment generating function of Bernoulli, can I derive the moment generating function for binomial? That's what I want to make use of that. Please pay attention. I need you to focus on the board. I told you where we are now. This is highly mathematical, intensive. So I need you to pay attention. You don't understand, ask question. Now, I want to do something now. I know the moment generating function of Bernoulli. I want to derive moment generating function for binomial. And, why do I want to derive it? And don't forget, binomial is a generalization of Bernoulli. Do you know that if random variable x followed by Bernoulli, okay, binomial is this. Please pay attention. X1, each of these is Bernoulli. If I sum Bernoulli in n time, it becomes a binomial. Does that make sense? If I sum Bernoulli, don't forget, in Bernoulli, it's just one trial. Is the trial number of trial in Bernoulli is 1. Okay, let me write so that I'm talking about Bernoulli. Okay, the numbers of trial is 1, but in binomial, okay, it's more than 1. So now what I'm trying to say, if each of these is Bernoulli, y is going to be binomial. Does that make sense? Now, if you want to go by this, and I said they are identically distributed, because take a look at this. This is Bernoulli, it means they are identically distributed and they are independent random variable. So all what I'm just going to do is to apply this. I'm going to just write this, mx of t raised to power n. So what I'm just going to do is just to raise this to power n. Okay, so I'm going to say, therefore, okay, that's going to be q plus p e t raised to power n. I'm done. This is a moment generating function for binomial. What have I done? Because I look at the relationship between the Bernoulli and binomial and apply that theorem now, and that is what I actually have. Okay? Now, and let me also tell you this. We can also, if I ask you to derive a moment generating function for binomial, okay, you can just go by this if you want. First start from Bernoulli and come here. You can also go direct. Okay? You can also go direct. You can also go direct. You can also go direct and find the moment generating function. What I just find here, take a look at this. Okay, for binomial now, if I want to go direct, okay, in binomial, if I actually sell f of y is n combination y, p raised to power y, q raised to power n minus y start from 0, 1, 2 to n. And I actually want to find the moment generating function, which is going to be this. And don't forget, binomial is a discrete random variable. So I'm actually going to have this. Y start from 0 to n. Take a look at that. Then here, I'm going to have y start from 0 to n, e raised to power ty. What is f of, what, oh, sorry, I'm dealing with y. What is f of y? So, n combination y, p raised to power y, q raised to power that. Okay, you know what I'm doing here? I'm going directly. I don't want to pass through by Bernoulli. Okay, you can decide to just pass through, you can, it's up to you, okay? Pass it to derive that. Okay, now, if you take a look at this now, then this is going to be, okay, summation y start from 0 to n, okay? Now, n combination y, take a look at this guy, you can combine them. This is going to be this, all raised to power y, this. Look at that, okay? Now, when you get here now, you actually need to recall that summation y start from 0 to n, n combination y, a raised to power y, b raised to power n minus y is a plus b raised to power n for maths. This occur, from binomial expansion, a plus b raised to power n is the same thing as this. Oh, let's compare this with this now. Okay, so if you compare that, okay, this n combination y, what is my a? Okay, so in that case, a here is this, right? What is your b? Your b is q. Okay, plug them in here now. What do you have? P, E, T plus q, which is this. Can you see that? This is going directly. This is passing through Bernoulli, applying this the independent law, the identically independent law. Okay? That's how that is done. Okay. At this moment, I can ask you to find